Okay, I'm going to go through a problem, simple machine problem here. I'm going to do it for a second class lever, but I'll show you at the end how it works for every kind of simple machine. So I've got a second class lever, fulcrum at the end. Remember FRE? First class lever has a fulcrum in the middle. Second class lever has resistance in the middle. Third class lever has the effort in the middle. So my resistance is in the middle. Okay, so I'm going to label this. You'll see over there, I have over here, I have to annotate and then list these different parts. So I'm going to do A and B here kind of all at once. So second class lever has a 420 pound box. So this is 420 pounds. And I have, it is 6 feet from the fulcrum. So from here to here is 6 feet. And then my 16 feet from the fulcrum is a handle. That is this right here. The whole distance is 16 feet. And so this right here, this is my DE, my effort distance. This is my DR, my resistance distance. You always measure from the fulcrum. Students will want to go here and here. From the fulcrum to my resistance, DR. From the fulcrum to my effort, DE. Okay? This right here, my 420 pounds, is my FR, my resistance force, what it is that I'm moving. Okay? So that's what I have here. So I'm going to list everything I've got here. DE is 16 feet. DR is 6 feet. FR is 420 pounds. And FE, we don't know. That would be right here. Can you see it right here? F, my effort force, I'm pushing down. Well, actually, I'm going upwards, so I would actually be going this way. Let's change my arrow. I'm pulling up on this to lift my box, so that would be going upwards, my FE. Okay? So that's everything I got. I do not know this, and we'll find that as we go along. Okay? So that's A and B. This is my annotate, and now I've listed, these are all my knowns. I pre-wrote all of my formulas over here, so you can refer back to them, and we can point them out. Okay? And so now we're up to C. This is an easy one. My IMA, we already know, is DE over DR, so 16 feet over 6 feet. My feet cancel out because mechanical advantage has no units. It's just going to be a number. Okay? When I divide that out, 16 divided by 6, I get 2.7. 2.66 or something. I round it off. So 2.7. That's my IMA. Okay? Then in D, part D, you'll see it says, what would be the ideal effort force to lift the box? Okay? This is where they always ask this in PLTW, and it's a confusing question. What it means is if there was no friction, if this machine was 100% efficient, how much force would you need to lift it? And that's this guy right here. This means my IMA equals my AMA, which is 100%. If these are equal, that's 100% efficient. Meaning, you know, these would be AMA over IMA would give you 100% efficient. Okay? So this is what you use. Now you can just plug into this. I'm going to do it down here. I'm going to isolate the variable because I like to do that. I'm going to move it out of this little box thing here that's in the way. And so I'm looking for my effort force, ideal effort force. You could write, I don't know if I can fit it in there. Ideal effort force. Okay? And that is going to be equal to, I'm almost at the FE comes over there. So it's going to be FR DR over DE. Okay? I just isolated the variable. I'm not going to go through the algebra steps to get there. Hopefully you can do that. If not, you could plug into these, and this would be your unknown. You'd have a number here, here, and here, which is what I'm going to have right now. So FR, 420 pounds. Okay? DR is 6 feet. And my DE is 16 feet. Feet cancel out. I'm left with pounds, which is what I want because I'm looking for a force which is measured in pounds. And when I do my math, I get 157.5, 157.5 pounds. If there was no friction, if it was 100% efficient, that's how much it would take right there. Draw a little box around my answers here. Okay? But in E, it says, it actually, when I actually did it and measured it, it took 185 pounds. Students will ask, where's that number come from? If I'm doing a problem on the board, I just say I made it up. I have to make sure that when if I'm making up my own problem, it's got to be greater than this, okay? Because then you're going to have AMA is going to be FR over FE, and my FR is the 420, and the FE is 157.5. Pounds cancels out, no units, and I get an AMA of 2.3. Okay? And I'm going to have to do my efficiency over here before I run out of room. Okay? So that's my AMA. That's my IMA. Efficiency. I'll write the whole word out. Is up here. AMA over IMA times 100. So 2.3 over 2.7 times 100. If this is not less than this, you did something wrong, because it means you're over 100% efficient, and that just ain't possible. All right, so when I do that, I get 85.2%. 85.2% efficient. That means I lost 14.8% of my force, of my effort force, was lost to friction. Okay? Okay, that's a busy page. But this works for everything. Okay? It doesn't matter what you're doing, and I'm going to show you, I'm going to make a clean page here. It doesn't matter what I'm doing. If I have an inclined plane and I'm pushing a box up my inclined plane, this is my FR, this is my FE. From here to here, that is my DR, because when I get done, that's how far I lifted the box, and this distance, the length of the ramp, can't see it, the length of that ramp is my DE. I pushed it, my effort pushed it this far, and then in the end, the resistance was lifted this high. If I have a wheel and axle, try to do this in 3 dimensions here. I have some string wrapped around it coming down here, and I have a box here. Here is my FR. So I'm turning my wheel this way. This is my FE. The ratio, this would be, if I'm doing it to the wheel, this would be my DE, and this would be my DR. I think it's the diameter or the radius, basically the same thing. Okay, actually it's related to the circumference, but it has to do with pi. All right, so it's a ratio there. If it is a wedge, I'm smacking on this with my hammer. This is my FE. Some force resisting it is my FR. Kind of hard to measure that. But the distance that I drive my wedge down, this distance, is my DE. I push the wedge down this far, and it splits my wood or whatever this far. So this is my DR. So you can see that those formulas work every time. I'm just having you just have to know where's your DE, where's your DR. That's really the biggest one. The forces are pretty clear. I'm moving something and I'm applying a force. So you just have to be able to tell, this is my DR, this is my DE, and so on. But as long as you do that, everything works out. Okay, so you only need one set of formulas, this one set of formulas here, in order to solve any of the simple machine problems. And that's what makes it nice. And so hopefully I think this will help. Because you can jump to whatever part you want, but it doesn't matter if I have, I'll do this would be let's see, if I have then my tweezers, that's a weird one. FRE. So I have my effort is like here. This is my, and I'm lifting a box here, and this is my fulcrum. Okay? So here's my FR. Here's my FE. It's in a different place. Okay, again, this, my DR, and this, my DE. So that's a third class. Class lever. I think I've covered everything I can do here now. So hopefully this will help. And of course, the pulleys, you just count the strands that are supporting and not changing direction. All right? So refer to this whenever you need to, and hope this helps.